Hey class, in today's lesson we're going to talk about probability, which is found in section 9.7 part 2. Our objectives are to find probabilities of mutually exclusive events, independent events, and complements of events. So mutually exclusive events are two events, A and B, from the same sample space. They're considered mutually exclusive if A and B have no common outcomes in common. So for example, what that would look like if I gave you a visual representation, it would be if I had a set A and a set B. And they come from the same sample space, but these are just two different events. And so what it would look like is that the probability of A, the letter U means union, so A union B would just be the probability of A happening plus the probability of B happening, because they don't really share anything in common. All right, the probability of the union of two events. So if A and B are events in the same sample space, the probability of A or B occurring is the probability of A union B, which equals the probability of A plus the probability of B minus the probability of A intersecting B. By the way, this notation here means intersect. Okay. So that means what they have in common. So then it goes on to say if A and B are mutually exclusive, then the probability of A union B equals the probability of A plus the probability of B. So this second one, more so this one here. What this would look like if I did a visual representation, we already did this mutually exclusive one on the last page, but the one above that, what that means is if they are not mutually exclusive, then that means you'll have some set A and then you'll have some set B, and it is all of them combined, so the set of everything combined. But the issue is that I have to subtract out this little middle section so that it's not duplicated. That's why it says minus the intersection of A union B, or intersection B. Okay? So let's take a look at an example to see what this really means. So in example 7, it says the probability of a union. So it says one card is selected from a standard deck of 52 cards. What is the probability that the card is either a heart or a face card? Well, let's talk about event A. So event A would be if you drew a heart out of a deck of cards. Now there are 4 suits in a deck of cards. So if I took 52 and divided by 4, that means there are 13 suits per deck of cards. So there are 13 hearts that are in a deck. Okay. For B, if I want a face card, well, face cards are ace, king, queen, and jack. And there are 4 per suit. So that makes, and actually they're not counting aces as a face. So we'll just say king, queen, and jack. And so that means that there are 12 cards per suit. I guess they're being pretty literal when they say face card. So to do this problem, it would be the probability of A union B equal to 13 over 52 plus 12 over 52. But then we have to subtract out the cards that are hearts but are also face cards. So of the hearts that are also face cards, it would be a king of hearts, a queen of hearts, and a jack of hearts. So that means I have to subtract out 3 of those 52 total cards. And so my total would be, if we're adding and subtracting, which means you go straight across, we would have 22 over 52, which is 11 over 26, or the probability would be about 0.423. Okay? And that means you have about a 42% chance of drawing a heart or a face card from a standard deck of cards. Let's take a look at the next one. All right, so it says the personnel department of a company has compiled data on the employees' numbers of years of service. It says if an employee is chosen at random, what is the probability that the employee has had 9 or fewer years of service? So what we would do is that event A would be the years from 0 to 4. which is 157 employees. Okay, and then event B would be the years that are from 5 to 9 years, and that is 89 employees. Alrighty, so the probability of A and B occurring would be the probability of A plus the probability of B, because these are mutually exclusive, and we know they're mutually exclusive because there is no overlap in their numbers. So the first event, 157, is 157 out the total amount of employees. So it's 157 out of 529 plus 89 out of 529 would give me 246 out of 529. And if we divide that out, that is about 0.465. So again, it's about, or very close to about, a 47% chance of, at random, selecting an employee that has had 9 or fewer years of service. And again, this is considered mutually exclusive because these two events are very clearly blocked off in their own segments. There is no overlap. And the last one with the cards, there was considered overlap because there are some cards that are hearts and that are face cards. All right, independent events. So two events are independent if the occurrence of one has no effect on the occurrence of another. And to find the probability of independent events, essentially what you do is you multiply their probabilities. So in example 9, it says a random number generator on a computer selects 3 integers from 1 to 20. What is the probability that all 3 numbers are less than or equal to 5? All right, so let's start with the first one. So our event A is a number less than or equal to 5. And so what that gives me, numbers that are less than or equal to 5 are 1, 2, 3, 4, and 5. Okay? So the probability, if I can, out of 20 numbers, the probability of selecting a number that is less than or equal to 5 would be 5 out of 20, which is 1/4. So then the probability of selecting my first number as a number less than or equal to 5 times the probability of my second number being a number less than or equal to 5 times the probability of my third number also being a number less than or equal to 5 would be 1/4 times 1/4 times 1/4, which will give us 1/64. So that is a pretty small possibility that if you had a random number generator to select 3 integers from 1 to 20 that happen to be less than or equal to 5. And again, these are independent events. One, it happening the first time has no effect on it happening the second time, has no effect on it taking place the third time. All right, so the complement of an event is, the complement of an event A is the collection of all outcomes in the sample space that are not in A. So the complement of an event A is denoted by A prime. So, for example, if I had a sample space, this is my entire sample space, but really I'm mostly just talking about A, okay? So the complement of A complement, is everything that is not in A, okay? So what we would do is we take the whole and subtract it from what we know A to be. So here's our last problem. So it says a manufacturer has determined that a certain machine averages 1 faulty unit for every 1,000 it produces. What is the probability that an order of 200 units will have 1 or more faulty units? So the first thing we want to talk about is that A should be a good unit. Okay, so the probability of A actually occurring. Remember, they said that there is one faulty one for every 1,000. So it must mean that there are 999 good ones for every 1,000. So the probability then of 200 good units taking place would be 999 over 1,000 times itself 200 times, or we can just say 999 over 1,000 to the 200th power. Okay, that would be about 0.8186. So then for us to ask the question, what is the probability that an order of 200 units will have one or more faulty units? That means essentially we're asking for the complement of it. We want to know how many, what's the probability that I'll actually get a bad unit. So this is, that 0.81 is the probability of getting good units. So the probability, so I'm going to write up here, so the probability of a complement, which is at least one faulty unit. So I'm just going to say one bad unit, would be 1 minus 0.8186, which is about 0.1814. So if we think about percentages, you have about an 18% chance of getting a faulty unit. All right, guys, that is the end of our lesson. Again, if you have any questions, please be sure to come see me for tutoring.